let's talk about decision trees. We saw decision trees before when we talked about diagnostic. We'll talk about a little bit more sophisticated version of decision tree when we have multiple stages. So it's a chain of events, and each of those events has uncertain outcome, and we're gonna describe this chain of events with uncertain outcomes using decision trees. So we start with the root branch of the decision tree, and in this example we have two possible outcomes, outcome A or outcome B, and then we have to specify probability for each of those possible outcome. And then for each of those outcomes, we have possible following events. So for if outcome A happens, then we potentially can have D, E, or F event happen. And then we need to specify probability for each of those events. And since we know that outcome A already happened, then all of them need to be conditioned on the fact that A already happened. So here we have to specify conditional probabilities. The same for this branch. For the branch of if B event happens, we have two possible outcomes, outcome G and outcome H, and we need to specify conditional probabilities for those two outcomes. And of course, the probability that outcome A and B, those probabilities have to sum up to 1 because one of them has to happen. And then conditional probabilities inside each of the branches also have to sum up to 1, because if we know that they already happened, then one of those three has to happen. So the sum of those three conditional probabilities have to be equal to 1. So let's look at a concrete example and see how we can apply decision tree modeling. So let's say you live in a house that is somewhat prone to mudslides, and each season there is a 1% chance that a mudslide happens. And you estimate that if it indeed does happen, then there's potential of 1 million in damage to your property. And you have an option of building a retaining wall that can stop the mudslide. It costs $40,000 to build such a wall, and it works in 95% of the cases. If mudslide happens and you have a wall, then in 95% of the cases, house stays undamaged. So the question is whether you want to build the wall or not. And also you have an option of doing geological survey. Geological survey might give you a better probability about the chances of the mudslide. And you might want to pay for the geological survey to make a better decision whether to invest $40,000 into the wall or not to invest. And we will answer those questions by using the decision trees and the Bayes rule. So let's formally set up the problem. We're going to build a decision tree. The tree will list the probabilities at each of the nodes. And the tree also will list costs associated with each of those branches, because you remember there are costs associated with losing the house if slide happens, building the wall. And then the goal will be to calculate an expected cost associated with each of those branches, and then we want to choose the branch with the lowest expected cost. So we want to minimize not just the total cost, but expected cost. Expected means cost weighted by the probabilities. So let's expected cost. Expected cost is the cost times the probability of occurring this cost. Okay, so that's, this one is measured in dollars, and this one times the probability of occurring this cost. So we'll do the example, and you see what we're talking about. Okay, so let's look at our potential decisions. So we have two choices: to build the wall or not to build the wall. And we know that building a wall costs $40,000. And if we do build the wall, then slide might happen or no slide happens, and we know the probabilities of those two events. They were given to us, 1% chance that slide happens. And in the scenario when you do have a wall and slide does happen, you also have potential two outcomes: that wall does work and holds the slide, or wall doesn't work and doesn't hold the slide. If it doesn't, you simply lose $1 million, so slide damages your property. And there is 5% chance that wall doesn't work. And in the case when you don't build a wall, so you just have slide, no slide potential outcomes, and again the probability is 1% and 99%. Okay, so let's start filling in the expected cost associated with each of those branches. We have, if the wall does hold, then we just lost. So we're looking at this branch. So we do build the wall, slide does happen, and the wall did work. Then in this case, we spend $40, but there's only 95% chances that we're gonna spend only $40, right? Because with 5% chance, we're actually gonna lose 1 million damage to the house and $40 that we spent on the wall. So if we calculate the expected cost associated with this branch of the tree, it's going to be 95% of the cases $40 is the only expense that we have, means the wall did work, and other 5% of the cases we're actually going to lose $1,040. Or million and 40,000, because this is the 40,000 is the cost of the wall and 1 million is the cost of the property damage. So if you combine those two together, you get $90,000 is the expected cost associated with this part of the branch. Now, so once we calculated this 90,000 here, let's look at this branch of the tree. So here we have slide, no slide, and slide happens in 0.01% of the cases. And we already calculated if slide does happen, there is $90,000 expected cost if this happens, right? So, and if slide does not happen with probability 95% of the cases, we just lose $40,000 that we invested originally into the wall. And if you combine those two together, you get this $40,500. And for this one, the calculations are rather straightforward. So if you don't build the wall, then with 1% chance you lose $1 million. And with 99% of the chances you lose nothing. So if slide doesn't happen, there's no cost associated with that branch. And so you have $10,000 is the expected cost associated with this branch. Now the decision is relatively simple. So you have two options: to build the wall, don't build the wall. An expected cost of building the wall is $40,500, and expected cost of not building the wall is just $10,000. So it seems like building the wall is not well justified expense. We basically spent $40,000, although there is only $10,000 expected cost of living without the wall. So that's pretty straightforward. Now let's say we have an option of doing geological test, and the cost of the test is $3,000, and the company that does the test gives us the following specifications of the test, the following parameters. They tell that our test, in fact, 90% accurate, meaning that if slide do happen, our test identifies it correctly in 90% of the cases, or if slide is to happen next year. So the test is trying to predict whether the slide is going to happen next year or not. So, and it's 85% specific, meaning that if slide is not to happen next year, then in 85% of the cases the test will come out to be negative. And the question is, so it's an additional piece of information that we get from the test. We have to pay for this piece of information. And the question is whether this cost is justified or not. Should we invest into this test? Seems like 3,000 is not that much, but let's do calculations and get specific answer to this question. So initial prior probability stays the same. Probability of a slide is 1% and no slide 99%. And if we try to calculate the probability of the true test, the total probability, we know how to calculate total probability. So it happens to be 0.1575. So you pay $3,000, and in 15% of the cases, the test will come out to be positive. And we will use this number later in our calculation, so we're just gonna remember it for now. So 15% of the cases that the test comes out to be positive. Now what we're really interested in probability of observing the slide, given that the test is positive, and its probability of seeing positive test given the slide, which we know that came from the specification of the company that makes the test, times the prior probability of the slide, and the total probability of seeing the positive test, which we calculated on the previous slide. And if you plug it in and get the calculations, so you have the probability of 0.05. So the posterior probability, you remember our prior probability of a slide was 1%, right, without the test. And once we did the test, and the test was positive, then the probability of the slide went from 1% to roughly 0.06 to 6%. So 6 times higher chances of getting the slide if the test comes out to be positive. And we can do the same calculations for seeing the slide if test is negative. And it happens to be actually a very low number. You remember that the slide probability is low to begin with, and now we get additional piece of evidence that test says there's going to be no slide, so you would expect probability to go down, and it actually goes from 1%. So we go from 1% to what we have here, 0.1 to 0.012%. So roughly 1/10 of a percent. So we cut the chances of slide happening by 10 if the test comes out to be negative. Okay, so let's start calculating expected losses. So let's try to calculate the probability that you lose everything. So you lose everything. If you decide not to build the wall, then the probability of losing everything is 0.05. This is in the case if we build the wall without doing the geological test. Then you remember that probability of a slide is 0.01, probability that wall doesn't work is 0.05. So probability of losing if you build the wall without doing a geological test is 0.0005. Okay. So let's look at the probability of losing everything if we decide to do geological test. Then there are actually two paths. So the first path is the test comes positive. Let's say our decision rule is very simple. If test is positive, then we build the wall. If test is negative, we do not build the wall. So if test is positive, then we do build. And then slide does happen, and wall doesn't hold. So, and another scenario when we lose everything is when test is negative and we do not build the wall, and then slide does happen, and we know the probability associated with each of those events. So probability of the slide of the positive test we calculated, and probability of negative test we calculate the total probability, and the probability of building the wall given the test is positive is just 1. So we always build if test is positive, and we never build if test is negative. And we know the probability of slide happening, and we also know the probability of wall doesn't if wall is not holding. So this is 0.95. This is 0.01. The same here, 0.01. So we can calculate total probability associated with each of those paths. And let's look at the cost of those paths. So the cost of this one, so since we did do the test, it's $3,000 here. And then we do build the wall, so it's another $40,000. And the slide happened and the wall doesn't hold, so that's another $1 million in damage. And here the costs are, we did the test, it was negative, so we paid $3,000 for the test, and then we don't build a wall, we don't spend money on this, but if slide does happen, then we're gonna lose $1 million in property damage. So those are the costs. Okay. So let's calculate the probability associated with each of those paths. Again, it's just a product of the probabilities. We assume those events are independent. So we get the probability for the first path of losing everything, probability of the second path of losing everything, and now we can just combine those things together. So probability of losing everything, given that we did perform the test, is just the sum of those two, so it's either one path or another path to happen, and so it's relatively low probability. It's 0.1%. Now let's do the risk reward calculations. Build the wall, not build the wall, do the test, not do the test. So we did the calculation of building the wall, not building the wall. You remember the expected cost of when you don't build the wall, slide happens with 1% chance, you lose $1 million, so $10,000 is the expected cost there. If you build the wall without doing the test, then it's actually $40,500. And if you do the test, I'm not going to do calculations here, but you can do it yourself. It's actually slightly above the option of do not build the wall. It's close to 1,100. And so this can be calculated from the, so we pay 3,000 for the wall. Then if test is positive, which we calculated 15% chance, we spend $40,000 on the wall. And then if actually slide does happen and the wall doesn't hold, or we didn't build the wall and slide happens, then we're going to lose $1 million. And so if we combine all those numbers together, we get to this result of 10,760. Now the question is, what do we choose? If you use purely utilitarian approach, then that should be our expected cost. But we have a low cost, but the risk is actually 10%. So you basically live in your house with the knowledge then 1% chance your house might get damaged on a given year. Now, this option, although it costs slightly more, so it's $760 extra, but you're actually reducing your risk a lot. You go from 10% risk to 0.1% risk. And you can think of this $760 as insurance premium. So you basically pay $760 to reduce the risk of losing large chunk of your property. And so now this decision is personal. It's basically how risk averse you are, whether you want to take a little bit more risk but minimize the expected cost, or you actually want to avoid risk as much as possible and you're okay to pay for it, $760, then you should prefer to do the test. So in summary, we learned in this section how to deal with uncertainty. And we use random variables to describe uncertain outcomes, and then to quantify those random outcomes, we specify probability distributions. They just assign probability to each possible outcomes for discrete random variables. In the case of continuous random variables, we assign probabilities to interval for that value. And we talked about joint and conditional probabilities, independence. Remember example of Sally Clark, who was accused. We talked about expectations and variances. We talked about specific distribution families like binomial and Poisson and normal. And we also learned how to do decisions under uncertainty using the expected cost calculations. And we saw quite a few examples of Bayes' rule.